Thank you, Theo. We move now to the first invited speaker of today's session, so Professor Arnulf Latz from DLR. So Arnulf, we are very happy to have you on board today in this artistic webinar series. Arnulf is doing really great work, very inspirational in the field of microstructure resolve modeling of lithium-ion batteries and also many other stuff. I mean, he's very productive scientist. Somehow we are doing complementary work, right? But both of us, we are interested on the mesoscale, right, from different perspective. And well, we are very much looking forward so listening to your lecture, Arnulf. Thank you for having accepted the invitation.
Yeah, thank you for inviting me. I hope you can hear me. If you could just give a short feedback whether this is working.
It's working perfectly.
Okay, great, good. So yeah, thanks for inviting me and giving me the chance to share with you some results of our recent research on structure function degradation relation. And when I listened to the first talk, I realized this is a real complementary talk to the first talk. I will say something about this microstructure resolve simulation and also the input, for example, we need, for example, in concerning the binder distribution. So originally, I also wanted to talk a little bit about our modeling approach. But I think to the broad audience, I rather decided to concentrate more on the results. And before I start, I really want to thank all the people in my group who contributed to that. Simon Hein, Timo Danner, Birger Rossmann, these are senior scientists, and PhD students, Fabian Singel, Lars von Kolzenberg, Linda Boley, Tobias Schmidt, and Igor Traskunov, all PhD students in my group.
Arnulf, we don't see the slides moving.
You don't see it moving, okay.
No, so we still see the number one, the slide number one. Fernando, maybe you can provide some assistance just in case.
Yeah. Well, let's try to stop the sharing again.
Yes, yeah. And then maybe you can share again. I mean,
yeah.
You should put the PowerPoint in slideshow mode and then sharing. So you should do in that order.
This is okay. This is what I thought I did.
Yeah. Let's see.
So then I will take a different route. Just a moment. Sorry for that.
Just maybe a short announcement. So yeah, if you want to attend tomorrow's session and Friday's session, remember that you need to register for those sessions. So registration is per day. Okay?
So can you now see my screen?
Yes, we see your screen. Maybe you can try to.
Yeah, can you switch one slide to see if it's working? Oh yeah,
perfect.
Now we saw the names appearing now in there. Right.
Fantastic.
Okay.
Wonderful.
Perfect.
Okay, good. Okay, so I hope it's now working. So let me say first something about my group. So I'm heading a department, computational electrochemistry at the German Aerospace Center. We are by now nearly 40 scientists and PhD students working on modeling and simulation of electrochemical storage and conversion system. The biggest part is still the battery simulation and modeling. So this is, for example, the understanding optimization of microstructure and function and lifetime. To do this, we need a very deep modeling approach to make sure that the things which we are predicting are really going to happen in reality. Therefore, we are taking very great care in developing consistent physics-based models for degradation mechanism, for example, and also theory of electrolytes. Of course, we are also working on post-Lithium system, which is not a topic of today, but we are integrated in the excellence cluster, the German excellence cluster, POLIS for post-Lithium system, at the University of Ulm and KIT. And then there's one part of my group, is still a smaller part, but growing, working with thermochemical storage, low temperature fuel cells, and high temperature electrolysis. So now let's go to the topic of my talk. So I want to talk about relation between structure, microstructure, inhomogeneities, and degradation and aging. Usually, of course, I cannot cover all the aging and degradation mechanisms. I will talk most of the time about SEI and plating, actually mostly plating and the influence of SEI on plating. Usually, there will be you will find a lot of model in literature where you develop models for doing simulation for plating, the simulation on SEI, here just a few names, and then mostly it's assumed that this is going to happen all over the electrode, since if you wanted, for example, to simulate what is the impact on the UV curves, for example, then it's clear that you measure the potential, you measure the current, and then you get a certain relation between them. You say these are changed by this degradation phenomena. But the point is, the reality is unfortunately different in electrodes, and you have seen examples in the first talk that the production process, for example, is of course not perfect. I mean, it's nearly to be perfect, we know that, but it's not really perfect, and there are inhomogeneity due to the process of production. Then during operation, you create inhomogeneities in the electrode, and therefore, for example, for the SEI growth, you find that the SEI is not growing homogeneously all over the electrode. And for the lithium plating, here a famous picture of the Harris group, you see that plating is starting at several places. Here, this grayish part is considered to be the plated lithium. Red and yellow are different stages of charge on the graphite. So this is far from being really homogeneous across the electrode. And what we are interested in is which factors are actually contributing to this inhomogeneities, or which factors are contributing from operation or from production. And even more important, how do they influence each other? If you initiate some degradation phenomena, you change the internal environment, the electrochemical environment, and this is changing the transport processes, changing the reaction, and most of all, SEI growth and lithium plating are influencing each other in a very subtle way, which I'm going to trying to present in my talk. But the question I want to address in this talk is, how do structural features influence the probability of degradation? How is the local dynamics influenced after the degradation was initiated? How can we simulate the dynamics of local degradation events, and of course their interplay, since this is to be a very exciting phenomena for me. And I will concentrate on lithium plating and SEI formation. As I said, I will not say too much about the modeling approaches, since they are sometimes too specific and too detailed. Only where I think it's necessary to say something on the modeling, I will mention a few things. So first, what is the model? What is the environment in which we are simulating? This is the software BEST, which I developed actually already nearly 12 years ago with my group at Fraunhofer at that time. It's a microstructural soft modeling approach which we developed together with Jochen Sausch of Fraunhofer from 2010 until 2015. The key features are that it's based on systematic derivation and numerical implementation of coupled, spatially resolved transport and electrochemical kinetics of lithium ions in cathode, anode, and electrode under the influence of electric fields, concentration, fields, and temperature gradients. This was the base model. It's now growing quite a bit after I moved to DLR, to the German Aerospace Center, where this software is now developed together with the Fraunhofer Institution. And we have implemented by now many extensions, being binder, influence of binder on electrochemical performance, plating, SEI growth. We are also working on solid electrolytes, or all solid-state batteries, grain boundaries in all solid-state batteries. We are now going into the modeling secondary particles and the influence on the electrochemical behaviors, and many more things. So I wanted to start with the binder, and actually it's a nice coincidence that the first talk was actually on binder migration and inhomogeneities to the production in this topic. This is a work in the collaboration with Marco Wolfram-Behrens. He talked yesterday also on thick electrodes, where we are collaborating a lot. So what they did were impedance spectroscopy measurement on NMC in a symmetric organization, symmetric fashion. This means both are really fully charged, so it should be a blocking configuration. And if you simulate impedance spectroscopy from microstructural simulation, we see that we get nearly a blocking, what you would expect from a blocking configuration. What you see in experiments are these the circles here, and you see that there is some kind of diffusional regime, and then you enter into the blocking regime. And what we realized is that we can capture this only by including the binder distribution in the electrode. And what even was more astonishing, that it mattered quite a bit how we distributed the binder in the electrode. Therefore, the simulations shown in the first part are so important. If you distributed them randomly on this tomography, which we had at our hands, we couldn't see the binder. So we only knew how much binder was in the tomography. Therefore, we decided that we just test different configurations. So we used a random one where the binder was distributed on the surface, and another one where we concentrated the binder in the contacts in the necks between pores. And this is, for example, is a picture of the binder distribution due to binder migration from the group of Schabel at KIT. And what we found is that depending on which distribution we choose, we get a different result for the impedance spectroscopy simulation. So again, the blue one is the pure tomography without binder. The random one, and mostly also the surface one, is nearly to be blocking, and only those which are concentrated in the contact were getting close to the experiment. So it was obvious that this macroscopic measurement signal was able to say something about what is going on microscopically in the electrode. And what was even more interesting to see, that if we wanted to predict the capacity fade, these are really thick electrodes, the capacity fade, and we tried to do the simulation without the binder, then our simulation, which are the closed lines, have been far away from the real simulation results. I mean, you could fit for small currents, but if you increase the currents by a factor of 10, we were far off the observed measurements. If you included a binder, of course, we haven't been perfect in agreement, as was pointed out. I mean, these are still modeling assumptions. And but the whole trend over a factor of 10 in the current density was recovered if we included the binder. So for the loss of capacity at large current, the binder was obviously a very important feature which we had to take into account if we want to understand what was going on in electrodes. So then, if we now do this and we want to see where is plating going to happen, so we had tomography from NMC, we had tomographies from graphite, we included the binder, we included carbon black, and then we simulated at which point in the electrode, in the anode under charging condition, we would get plating. At C/10, you basically, everywhere where you see a vertical line, you will find plating, and the color corresponds here to the current density. So for the two lowest current density, C/10, C/5, we didn't observe any plating until the cutoff voltage. If we at C/2 already, we saw slightly above the cutoff voltage plating. At 1C, we lost a lot of capacity, and over a large range, we found somewhere in the electrode plating. And if you get to 5C, for example, it's not even in the plot anymore, since we get immediately plating all over the place. The interesting question is, of course, where does this plating going to occur? And here you see immediately the impact of the inhomogeneities, which I mentioned in the beginning, which were produced due to this operation. If you look here at the electrolyte concentration distribution, you find enormous depletion of electrolyte in the anode regime, since basically upon charging, the anode is sucking up all the lithium ions, and there are only some lithium ions remain and close to the separator. Everything what is produced here in the cathode is not fast enough transported to the anode, and therefore the only charging is going to happen in a small range close to the separator. So basically, instead of having the full capacity of a big, thick electrode, you have basically just 1/6 of the full capacity available, and this is immediately charged at high charging rates. Here you see that the plating is really going to happen. This is a bluish area most of the time, bluish blue and yellow, that is close to the separator. So here the inhomogeneity, which is causing plating, is due to the operation under a situation where you wanted to have a high energy density electrode, but you couldn't do it since the power density is not available due to transport limitations. Of course, you can do something, and this is what we did afterwards, namely we're doing the sign simulation. So one of, you will see you have inhomogeneities, and now you start to fight inhomogeneities with inhomogeneous design, which is one solution. Here experiments from Chen. Again, thick electrodes without laser holes drilled into the electrode. You find plating, as we find in our simulation. If we are drilling holes into our virtual electrodes, we see that there is no plating anymore at the separator, and the same is found also in experiments. So in this sense, we can, one lesson is you might be able to accept inhomogeneities under operation, but then you have to do something in the design, namely trying to choose the proper inhomogeneous design to fight the inhomogeneity due to the operation conditions. Now let's look a little bit closer to what is happening during the actual plating event. So far we just tested where is plating going to happen. Now we are really simulating plating. So we are not only saying it's going to happen at a separator, but we simulate how much lithium is deposited and how much lithium is stripped if we change the current. So, and of course, one interesting thing, since you cannot look into the operation of the battery, is do you have some macroscopic features from the voltage time curves, for example, or voltage SOC curve, which gives you an indication that you have plating. And what you see here is that, yes, at a certain point where you get a plateau, you have plating. This dotted line is the simulation without the plating mechanism implemented. And you see already deviation from the actual mechanism without plating way before you find the plateau. If you go in the delithiation, so the oxidation regime, you do stripping, deintercalation of the anode, you find the stripping plateau, which is sometimes used as an indicator for plating. And then you, at this point, all the lithium is resolved, and you find again the OCV or the voltage of the graphite. And here is what you see at the end, the plated lithium at the end of charge. And you see that again, it's mostly at the separator, but you see also it's not homogeneous. There are some, some particles are covered by a thick plating film, some are only a very thin, relatively thin plating film, via nanometers regime. So the inhomogeneity which we saw in the Harris picture are already indicated here in this picture. And I will later on, at the end of my talk, say a little bit about how important the shape of the particle is for understanding where plating is going to happen. So the largest deposition of plated lithium is at the separator, and we have an inhomogeneous thickness of the plating film. So this was again simulated with a homogeneous SEI. Now I want to give a motivation why we cannot expect to have a homogeneous SEI. Oh, no, let's go more detail about the stripping situation, since there's something very interesting going to happen. Again, here are the simulations for plating, here are the simulation for stripping. This, the red one is the part that is directly intercalated, and you see that the plating degree is slowly increasing, and at some point you have no intercalation anymore, and you have a full plating regime. So this is exactly here. You have plating at the green part, intercalation at the blue part, or if you now consider the current which is going into the plating, you have no plating in the green one, here just intercalation, and full plating here in the red part. More interesting one is the stripping situation. So here we are now at that situation, and what you see here is very amazing. You have a plated film, you turn around the current, you strip your plated film. Eventually, all the lithium is resolved. So all the lithium is again in solution. But what you see is that you get a very inhomogeneous picture. You don't have only stripping. You have also parts where you have fully intercalation, and only here you have de-intercalation. So what is going to happen here actually is you dissolve your lithium, increasing the lithium concentration in the electrolyte a lot. This causes an intercalation in some part of the anode, although you are globally under a de-intercalation condition. And this effect, the phenomena, leads to the fact that the length of the stripping plateau, which is sometimes assumed, is not really indicative for the amount of lithium you have plated, since some of the lithium which is going into the solution is immediately re-intercalated in the graphite. So you have a mixed situation, stripping, intercalation, de-intercalation at the same time. So the length of stripping plateau does not correspond to the amount of plated lithium. So this was a simulation with a homogeneous SEI film. We developed in the recent years, starting actually from 2015, a very detailed picture for SEI growth. We very detailed compared different mechanisms for what is responsible for the SEI growth, electron conduction, electron tunneling, solvent diffusion, and some mechanism which was motivated by DFT simulation of UG, who said that there is one mechanism which has to be considered, namely a interstitial mediated transport of lithium, of quasi-neutral lithium from the electrode across the SEI to the electrolyte where the electrolyte is reduced. So I think I think I cannot really go into the details here. First, I want to say the most favorite one which we found is the lithium interstitial diffusion. The reason is that we had experimental results from the group of Professor Jossen at UTM Munich, who made aging experiment for calendar aging experiments. So he stored graphite at different state of charge, and he measured how much capacity was lost over 1 year. He found this stepwise curve. And if you try to recover this stepwise curve, we can, since we know all the potential difference for the different mechanism I indicated, we can see that only the mechanism producing the interstitial mediated transport mechanism can really reproduce exactly the observed behavior. And the reason is that we have this exponential behavior where the OCV, so the potential difference between the electrolyte and the electrode, is entering. And this strong dependence on the overpotential is responsible for a stepwise graphite stepwise decay, and this is exactly the layered shape of the staging behavior of graphite during discharge or charge. And we transformed this into a model for not only calendar aging but also for cycling. And we found that if we include this interstitial mediated transport, that we can recover the asymmetry of SEI growth during charging and discharge. I mean, the physical reason being that you get a larger, way enhanced increase of SEI growth during charging is that if you charge, the electrons are basically transported toward the electrolyte, and if you discharge, the electrons are transported to the outer circle. And this bias causes that you create more interstitials during charge than during discharge, and this makes this asymmetry. Again, here we have this very huge dependence on the potential and the overpotential, and which I'm going to show now is that this huge dependence on the overpotential is responsible for an inhomogeneous SEI growth across the electrode. So we did implement this model on our microstructural simulation, and what we found is actually for the cooperation with the JAXA, this is the Japanese aerospace agency, who had a battery in space for 15 years in the Raimei satellite, and we investigated their data. And what we found is that if we simulated the SEI growth during different depth of discharge and at storage, that we find a huge inhomogeneity of the SEI thickness across the electrode, which we did already in 2018, which was done in the PhD thesis of Tobias Schmidt. And there are huge differences in the thickness in the range of several nanometers, sometimes tens of nanometers. And I say this number since what we now did for understanding plating is that we considered what is going to happen if these inhomogeneities of the SEI are adjacent to each other, which we have seen in the previous picture. So we considered an artificial regime, namely here a thick SEI and a thinner SEI, difference about 5 nanometers. And then we compared how is the plating going to happen if we compare these two situations, homogeneous one, which is the orange one, and the inhomogeneous situation. And you see that in the inhomogeneous situation, the drop in voltage is much bigger, so the amount of overpotential produced is much bigger than in the homogeneous one. So it's not surprising that we get a bigger drop in the overpotential, since there is a part which has a larger interface resistance and the SEI is thicker. What is amazing is that the change, or the plating, is going to happen much faster, since you reach the plateau regime in a very much shorter time than if you just stay in the homogeneous regime. And not only that, you also see that the amount of lithium produced is much bigger in the homogeneous simulation, which is this one, compared to the inhomogeneous one. So you could argue, well, this is also not surprising due to the larger interfacial resistance, but you also see that in the part which has the same interfacial resistance as the homogeneous one, you get a larger amount of lithium plated, and this is due to a very subtle interplay between overpotentials, interfacial resistance, and redirections of currents. So what we observe in this situation is that we get first plating in the part which has the largest interfacial resistance, or the thicker SEI, and of course there the amount of lithium plated is much thicker than in the part where we have a thinner SEI. But if we just have a small hole with a smaller SEI, the current is redirected to this region such that the current density is increasing so much that the corresponding overpotential is producing the plating in the part with the smaller SEI. So the message here is that you really have to consider the structural configuration to see at which points you get the plating and when the plating is going to start, and how, due to the production of plating, the currents are redirected in the electrode such that you might get earlier in some parts plating compared to the situation which would be completely homogeneous. So it's a very complicated situation, it's very subtle, but it's going to be more interesting. So with our colleagues from ZSW, the group of Margaret Wolfhard Mehrens, they made a very interesting experiment. They studied a graphite electrode. They wanted to understand how is pre-lithiation influencing the behavior under open circuit potential conditions. So they implemented physically a plate of lithium on top of the graphite. Then they wrapped the full configuration in a separator, and they had a counter-electrode which was just lithium. Here are the experimental conditions. So this is how the experimental experiment looked like. Here's the plating, here's the lithium, this is the graphite electrode. And then they observed the full system just under OCV conditions. So there were no external current flowing, just OCV in a pouch cell. And they observed this with different experimental techniques, closed discharge, optical emission spectroscopy, GDOS, and Raman. And we simulated the whole situation. So what we did is we used this lithium disk, put it on graphite. This is how it looks from the back. Then we also used the separator, and we put a counter-electrode lithium on the other side. So there were interesting results on how the lithium is dissolving. I mean, why it's dissolving? Dissolving is that you have directly two conductor on top of each other with different Fermi levels. And this different Fermi levels means that you get an electronic current from the lithium to the graphite. So you dissolve via this process lithium in the electrolyte. The electrolyte is diffusing through the lithium is diffusing through the electrolyte and is intercalating into the electrode, in the graphite electrode, which you see here in the potential signal. So this is no current, no external current, just this lithium on top of graphite. And you see the stages of graphite. So this is the part where the disk is dissolved. Then you have a relaxation regime where you reshuffle the lithium in the electrolyte and you deposit somewhere else. And then you are in equilibrium situation. So far, this was a very interesting result, but then it became more interesting when we observed what is going to happen with the counter-electrode. Again, I want to remind there is no external current flowing, so in principle, the lithium disk on the counter-electrode should not be affected whatsoever. But our simulation showed a very interesting feature, namely that suddenly on the counter-electrode, you found exactly opposite to the disk, a enhanced deposition of lithium and a reduction of the lithium on the rest of the counter-electrode, which was exactly observed also in the post-mortem image in the experiment. So what was going to happen? What was going to happen was that since the lithium disk was dissolved, we had a concentration gradient in the electrolyte. The lithium ions were diffusing to the counter-electrode, where due to the larger concentration, you suddenly were not in equilibrium anymore. You could deposit lithium, and since you have to make sure that the charge neutrality is conserved at the other part, namely here at the border, lithium had to be re-dissolved into the electrolyte so that the full counter-electrode kept charge neutral. And this lithium then was traveling back to the graphite and was intercalating there. So in total, no lithium was really taken away from the counter-electrode. It was just reshuffled in the counter-electrode. And to demonstrate that this really is important, how the counter-electrode looks like if the cathode is inhomogeneous, we used a different setup, namely here is the first setup, and then the second setup, we concentrated the counter-electrode to the small strip here at the bottom. And here you suddenly get a huge difference. For the small counter-electrode, there was a very smooth dissolution, this very smooth degradation of the cell potential. There is no stepwise intercalation and reintercalation and relaxation. And also the fraction of lithium disk was dissolving much, much slower for small counter-electrodes. And this means that the smaller counter-electrode had a significantly influence on the dissolution rate of the lithium disk. And if you now think, and this is a nice picture on how different the lithium concentration in the electrolyte is for the small counter-electrode compared to the large counter-electrode. And if you now think what is going to happen in a lithium plating event where you have a counter-electrode, a real cathode, and you keep it in an open circuit situation, then you know that also is something going to happen really non-locally on the cathode. And another problem, for example, is, or another interesting question is, how does this, usually this this bigger anode, which are just very often used compared to the cathode, how is this asymmetry influencing the cathode due to this very non-local phenomena? So the last seven minutes, I want to share with you some some new results based on some older simulation which we did in 2015, and I want to explain this slowly. So what we did was the following: we created actually an artificial geometry, so Jochen Sarge and me, and then we did actually at that time thermal simulation. Therefore, you see here the overpotential, and here the production of Joule heat at the interfaces due to intercalation and deintercalation. And and what you see here is this scattering event is if we do cuts at each point of the cathode, so here, and look what is the value of the overpotentials, the average value of the overpotential in this layer, then we find this extremely scattered events. The same then for the production of heat. If we do a running average over this scattering plot here, we find this red curve, and then we compared with the P4D model. So we did a upscaling of our model, and we had an exact upscaling procedure, and we simulated the same porosity and the same tortuosity, so the same picture with the same material parameters with the P4D model, and then we found a very good agreement between the running average and the P4D model. But there remained a huge scatter, and this is really huge. If you see here, this is a volt. So we have here minus 0.3 volt, and we have scattering events going up to 0.1 volt. So changing the sign, going up in voltage. And this means in the overpotential, you have enormous fluctuation. And if you think that the SEI growth, for example, or plating is something which is going to happen locally, then these fluctuations are of enormous importance, but they are not captured in the standard P4D model. So if you do cell simulation, I mean, this is very often done to see at which point do you get plating. Then you would do a P4D simulation, human model, and you find, well, yes, you are safe, but then you do the microstructural simulation, you see, well, maybe there are potential fluctuation, or at that point, which are really going to maybe too low, and therefore causing a plating event, which is not covered by the P4D model. So with Igor Traskunov, my PhD student, we did a very careful homogenization ansatz, a very careful analysis of what was done in the literature. And then we came up with the following idea, which we transformed into a rigorous mathematical upscaling procedure. Namely, the shape of the particle is a very key factor. Not only the shape of the particle, also inhomogeneous binder covering will produce overpotential fluctuation in the same order as the average. And they cannot be discarded if you want to predict the plating events or any other degradation phenomena. The reason is that even under homogeneous situations, you will, due to the different curvatures, have a stronger increase of concentration at a part with a larger curvature and smaller increase in regions with a smaller curvature. Of course, there's diffusion. And at some point, you might say, well, you might get wipe out all the gradients. But under steady state, we see that these gradients maintain, of course, the charge and charge. At some point, they are erased. But this non-homogeneity is the major source of these overpotential fluctuations. And what is most amazing, originally I thought maybe this has to do with some electrolyte concentration gradients, but this is of second order. On first order, 0th order, the same order as the P4D model, we have this curvature contributions or the shape influence. So the statement is, if you do homogenization and you go to the average spherical particle approximation, you lose physics, which is of the same order where you want to get your result on. So the non-homogeneous environment, electrolyte binder, and so on is crucial. And we cover this in our 2 published paper, and the mathematical paper will follow soon. And not only that, we also said we want to keep the possibility to do efficient mesoscopic cell simulation. And therefore, Igor invented a model which allows to with the same numerical efficiency, allows to simulate the cell scale, but gives information on the amount of potential fluctuation which you might expect in microstructural simulation without doing the microstructural simulation. That's the point. And what Igor found is that there's a one-dimensional parameter which has to be considered in addition to the usual parameter. This is the derivative of the Faraday current with respect to the concentration, which is proportional to the concentration dependence of the overpotential. So there is a difference whether you have LFP or whether you have LCO, or there's a difference whether you are in the flat regime of the graphite OCV or in the regimes where you go from one plateau to the other. In each of the regimes, you will get different overpotential fluctuations and different probabilities of SEI growth, of different probabilities of plating events. So we have this, as I said, is a rigorous model. It's a rigorous upscaling procedure. We have semi-analytic solutions for the fluctuations on particle interfaces, and we have shown that it can be calculated now as efficiently as the P4D bottle, but gives in addition these the size or the scale of the expected fluctuation and therefore the probability of degradation events. So again, therefore, what I mentioned before, we have not yet completely fully studied, but this is a real good probability that this inhomogeneity, which is observed here in this experiment, might be exactly due to the inhomogeneity here in this graphite graphite particles, that you get different overpotential at different parts of the active particles, and therefore the plating event is not homogeneous. There are different reasons to contributing that. I mean, the inhomogeneous SEI is another one, which I showed, but it's just the pure shape of the particle alone which can already give rise to such inhomogeneities. And here to show that these fluctuations, this very random looking like fluctuation, are really due to the fluctuations which we observe at on particle scale. So Igor did this very artificial regular configuration here, where you see fluctuations of the concentration, fluctuations of the overpotential, which are of course the same oscillatory way which you have here. But if you then choose an irregular situation, you get basically a superposition of all this particle origin and fluctuation, and you can. I mean, of course, I mean, we didn't try to recover exactly what we did with Jochen, but you see that if you wouldn't know that this is coming from this regular shape, if you just look on that, okay, here you see again minimum, but if you just look here in the middle, you would say, well, okay, this looks extremely random, but it's nothing else but a superposition of single particle fluctuations, which you can exactly predict. And this is what I said before, that depending on which is the SOC, here we have against time, we have a fluctuation in the overpotential, which gives rise to, here is the overpotential is double as high as it is here. So it also at the stage where you are will influence whether you get more likely or less likely degradation phenomena. So with that, I'm at the end, I'm coming to my summary. So what I tried to convey is the importance of looking at inhomogeneities in the electrode, either due to operation or to production phenomena origin. They will enhance the degradation, at least for standard designs of electrode and cells. And if you have this degradation due to inhomogeneities, you might think about the inhomogeneous design to overcome this. And again, here simulations are very important to find the right design. I emphasized how important it is to look at the binary distribution. They're highly relevant for the macroscopic impedance. I pointed out that the potential, so that the specific transport mechanism, which leads to the strong potential dependence, will lead to inhomogeneities in the thickness of the SEI on cell level. The inhomogeneities again enhance the tendency for plating. Inhomogeneous plating again give rise to non-local relaxation phenomena on the counter-electrode, for example. So suddenly you do something on the anode and you influence the whole inner environment of the battery. And then the interplay of particle shape and SOC dependence on OCV give rise to large overpotential fluctuation, which makes it necessary, if you want to understand also degradation phenomena with mesoscopic homogenized theories, you have to do something more, and we try to go in that direction. And at least we offer one solution, which of course has to be improved, but which is at least a proposal for a solution. And we did this with rigorous homogenization procedure. This was developed to capture this yet unaccounted overpotential fluctuations efficiently in cell scale simulation. And with that, I thank you for your attention. I thank all the people with whom we collaborated. I want to mention also the CMET Graduate School at KIT, where Igor is included. Of course, I want to thank our ministry, the ProCell cluster, in which we did this nice collaboration with the ZSW, and want to thank my colleagues at ZSW, the Center for Electrochemical Storage, and of course the University of Ulm, my colleague Volker Schmidt, who did this extremely exciting microstructure reconstruction in his research. So thanks
Thank you very much, Arnulf, for the wonderful presentation that highlights very well the importance of accounting for the electron microstructure in the modeling analysis, but also an experimental analysis point of view. Thank you very much. It was really great. So, Fernando, we move to questions, maybe? Yeah.
Absolutely, yeah. Here we have many questions for you, Arnulf. So here we have Susan Hamadi, who asks, regarding SEI evolution, while it is indeed interesting to simulate the thickness as a function of applied voltage and time, we want to capture the microstructure evolution of a dual phase SEI. How would one gain a more chemical understanding on how the SEI grows and evolves over time?
Yeah, thanks for this interesting question. I didn't have time to go into that. Actually, one of our first papers in SEI growth were exactly dedicated to how the solvent, the solvent composition, or the composition of the electrolyte could be responsible for this dual layer growth of the SEI. So we showed we actually developed a model which allows us, first of all, to simulate a porous SEI to predict the porosity of the SEI dependent on the transfer properties of the SEI, and only if we considered, for example, a mixture, a solvent, the usual standard solvent mixture for electrolytes, DMC and EMC, with a different reduction potential, we saw that this different reduction potential gave rise to a dual layer structure, which was growing in a very correlated, consistent way. You might look up our paper from, I think it's 2017 paper in PCCP, where we developed the theory and showed the results on that.
Great.
Thank you. Well, here we have another question from Mehdi Chuchan, actually our next speaker, that asks you, you mentioned CVD coverage has a big impact on the SEI formation. In your opinion, is it due solely to the loss of active surface area, or is it because of a better access to electrons?
Well, this is a good question. Actually, this is one question I want to study with another PhD, which is also in the CMET colleague. I can't give right now a definite answer. I think, as I showed, the SEI, the coverage will lead to the potential fluctuation. This means, of course, that this overpotential fluctuation, which are also responsible for the SEI growth, is of course influenced by the coverage. But you're right. I mean, this is a carbon binder domain. This means the carbon within the binder might lead to the fact that you have a larger interface with the electrolyte, and therefore you create a SEI within the carbon binder domain, coupled then to the graphite, which is changing the structure of the SEI. This is something we have to discover now. So my best answer would be, I think everything you have mentioned could be relevant for the different SEI growth depending on the binder coverage.
Thank you for your answer, Arnulf. Here we have another question from Avos Shodiev, another one of the artistic folks. He says, have you ever tried divide carbon binder domain into two separate phases in your simulations? In your opinion, can this approach give us new insights?
This is exactly what we want to do with my new students, Modular, that we want to go into more detail of this carbon binder domain. We want really to take these domains apart, so the binder part and the carbon part. We want to understand how the so to say mixed ionic electronic conductor is evolving depending on the microstructure of the carbon binder domain, and exactly want to study whether we maybe have forgotten something in our upscaling procedure. Right now, our carbon binder domain is an homogenized average domain which has electronic conductivity and ionic conductivity, and we do phenomenological ansatz there. I personally want to understand with Modular this question deeper to see whether we can, if it's just to know or to understand how we have to design the homogenized model depending on how the binder and the carbon is mixed within the carbon binder domain. This might already be very important to see what this could have an influence on SEI growth, on plating, on the impedance, and so on.
Yeah. This is very challenging to be resolved at experimental level, right? I mean, to see where is the carbon, where is the binder, and so on.
Exactly. Yeah, that's the hard point. Yeah.
So here we have final answer. Sorry.
Yeah, maybe I may ask a question. A short one is regarding the the separator, Arnulf. Maybe I missed that. So are you considering an homogenized model for ticket to call? Okay.
Yeah, it's the I think, but I mean, we in the very early time of our simulation, so I think 2010 or so, we tried to resolve the separator, and we did it there. I think there are some questions which might be interesting, especially if the pores. If the pore size are comparable to what is going on, well, of the pore size in the electrode, then at the interface you might have a mismatch of the pores in the separator and in the electrode, and this might be another reason why you have a stronger initiation, for example, of plating at the interface. So this is an important question, I think.
Great. Okay, Fernando, I think we should. It is still a question pending.
Yeah,
we can take it because we have time.
Final question before moving to the next speaker. So this is a question from Seliang Su, following up on a previous question from Susan. Here the question is, could you please give a bit more details on how you implemented the plating and stripping process and the SEI growth? Yeah, big question.
This is a hard question. I could give a full morning talk about how we did the implementation. So first of all, I mean, what we did is the following. We developed first on the 1D scale the model, and there we did the implementation within MATLAB. So this is we have transport, electronic, ionic transport, solvent transport, and convection actually in the solid electrolyte phase. And then we have degradation phenomena. And this can all be coupled in this 1D model. If you go to the 3D structure, we keep it locally 1D. So we have basically an interface in our software. We have a structure, so a software structure, which allows us to do modeling on each of the interfaces between an electrode particle and the electrolyte. So we can basically resolve with all the interfaces which we are resolving the particles, we can do exactly this homogenized modeling in a 1+1D fashion. So, but you have neighbor parts of the then have a different behavior since the SEI is evolving differently at each point. So this is how we did it from a software point of view.
Okay, wonderful, Arnulf. Thank you very much once again of having accepted the invitation, of being with us today. Thank you for your huge contributions in the field, and very much looking forward the next time, your next papers and so on.
Yeah, thanks for inviting me. Yeah, thank you.
Thank you, Arnulf. Thank you very much.